Hello, these are some lectures on a subject we've called pistonics, or ideal gas thermodynamics explained. And I'm John Perham from the University of New South Wales.
And I'm Eigil Præstgaard from Roskilde University.
Okay, so these lectures are based on an article by us two and Edgar Smith with the following title, and there's the reference, which we published in honour of our friend and colleague Professor Edgar Smith from La Trobe University, who died tragically before his time in 2009. And like us, Ed disliked the demathematization of elementary physics, believing that students are more confused than enlightened by the replacement of mathematics by glib arguments described as physical intuition. And this article had its genesis in 2000 when John Perham was a visiting scholar at La Trobe University, and when the ever-satirical Ed coined the epithet pistonics to describe elementary thermodynamics. Since then, Eigil joined the party, and the project was finally completed to our satisfaction last year. Well, the discovery of the laws of thermodynamics and their application to building heat engines initiated the Industrial Revolution, the age of rapid transport, and the production and distribution of electricity. A key part of the story is the concept of temperature, whose formal definition, believe it or not, first happened in 1968 with the adoption of the Kelvin temperature scale. And this is based on a thought experiment called the ideal gas Carnot cycle. In this treatment, we will follow the usual steps, but avoid tautologies and forward references found in standard treatments. The entire treatment is done using only mathematics from the freshman curriculum, which enables us to consider the problem of how real apparatus can be engineered to simulate the ideal apparatus of the Carnot cycle. Okay, sorry about that. Anyway, let's start with a brief history of temperature. We all have a subjective feeling of hotness and coldness due to the fact that some of our nerves fire when in contact with hot or cold objects. But it took several centuries involving some of the giants of science before a precise definition of temperature emerged, with the surprising insight that there is a degree of coldness called absolute zero which cannot be exceeded. We begin the story in the late Middle Ages with the invention of the thermoscope. So let's have a look at it. The early attempts to build a thermometer were made by Santorino and Galileo, involving an apparatus rather like that shown below. So let's see if we can get most of it. So there's water in here and there's air in here. So the idea is that as the air in here heats up, its pressure increases, and this will force the water down and then up the other side, and so that should be a measure of temperature. Unfortunately, of course, it will also be affected by the external air pressure. So this is not really a thermometer, but a thermoscope. But it gives a rough idea of what temperature is. Now we come to thermometers. And most subsequent attempts to build real thermometers were based on the observation that hot fluids occupy more space than cold ones. An exception to this is water, which, as it is heated from its freezing point, actually contracts until it reaches its maximum density at 4 degrees Celsius, depending weakly on the atmospheric pressure. Anyway, after visiting the famous Danish scientist Ole Rømer in Copenhagen, Fahrenheit, who I think came from Poland, produced a mercury capillary thermometer, whose scale was named after him and is still used in the United States. In his scale, the temperature of a saturated water-ice-salt mixture was taken to be 0 degrees Fahrenheit, and the temperature of a healthy human to be 96 degrees. So that means that the boiling point of water will be roughly 212 degrees. Soon followed the Celsius scale, in which water boiled at 0 degrees and melted at 100, which was soon inverted by Linnaeus, who swapped the endpoints. So now we go on to the nature of heat. But all these operational definitions dependent on the assumption of a linear relation between the volume of the working substance and the temperature of intermediate points. The situation at that time was further confused because no one really knew what heat was. Most people believed it was a substance called caloric, which moved between bodies as they were heated or cooled. A contrary view was provided by Count Rumford, who, while working as armourer for the state of Bavaria, observed that if a cannon was bored in water, the water eventually boiled. Since the properties of the metal appeared to be unchanged, he concluded that the production of heat had something to do with the motion of the drill. We can observe a similar phenomenon by observing that when inflating a bicycle tyre, the pump actually appears to become hotter. And this led Joule to propose the equivalence of motion and heat, finally convincing William Thomson, Lord Kelvin, of the incorrectness of the caloric theory and the need for an absolute temperature scale independent of any working substance. Kelvin noted that the volume of gas in a gas thermometer was measured as at the two revised Celsius fixed points, and it was supposed that the volume was a linear function of the temperature, that the value would extrapolate to zero at some finite value around about minus 270 degrees. He proposed that if amount of heat moved from a body at temperature T to one at temperature T minus 1, the maximum amount of work which could be extracted was independent of T and the substance involved. And this process is implemented in the Carnot cycle, the Carnot cycle, which is a theoretical heat engine, and as we will see, leads to a proper definition of temperature and the limits imposed on the efficiency of machines and energy conversion imposed by the second law of thermodynamics. As the reader may have discerned from above, the path to our understanding of temperature and the conversion of energy from one form to another has been a long and complex one which is still going on. And this may account for the range of treatments, the number and range of treatments of the subject, which go from the highly axiomatic and mathematical to the oversimplified versions found in undergraduate physics books. And this complexity is increased because of this close relation between thermodynamics and statistical mechanics, a branch of mathematical physics which seeks to calculate the properties of macroscopic matter away from the properties of the molecules of which it's composed and their interaction. And this presentation seeks a middle way of restricting the level of mathematics to knowledge from freshman calculus, at the same time avoiding forward references to theorems in statistical mechanics. So this learning material, this Mathematica notebook is the learning material for some online lectures or for these online lectures on ideal gas thermodynamics, which can be downloaded from YouTube. And novel features include a new treatment of the kinetic theory of the ideal gas using a spherical container and avoiding assumptions of equipetition and the ideal gas equation of state, a treatment of the Carnot cycle from which the concept of temperature emerges in terms of the efficiency of a Carnot engine rather than assumed using the ideal gas equation of state, a treatment in terms of differential equations rather than the traditional differentials, since the latter are not part of the freshman calculus curriculum, and finally an investigation of Feynman's speculation on the temporal behavior of quasi-static processes, showing that these can be engineered for real isothermal and adiabatic apparatus using simple control laws. And as we said before, this material is based on the article we discussed earlier. So I think we'll hold a pause there and come back and continue in a little while.